which I probably shouldn't be that way, but I am. But in this course, I kind of have to be, because you don't have a good reading source. So when we get into physics, there's a whole chapter Dr. Welliver wrote in Nagelhout that I give you. Now that, I'll pull questions right out of that reading, because that's absolutely required reading. But my point being, if you want to prepare for me, the best thing you can do is if you can understand and explain anything on my slides and everything I said, because sometimes I say things and it's not on the slides, you should be okay. All right? So, all right. So organic. First of all, organic in chemistry does not mean organic in the health foods world. And this is a big problem for me when that buzzword first started coming around, because I'm like, whoa, are you trying to tell me that carrot over there isn't organic? There's all sorts of organic compounds in there. Oh no, that's not organic. You need to buy our organic. Well, in the healthcare world, organic is more of a non-regulated term. That means that it's more healthy the way they produced it, less pesticides, less this, less that. And really, is there really any true rule for what organic means in the health food world? Not really. But when it comes to chemistry, organic means it's a carbon-based compound. It's not quite that simple though, because if you take a bunch of carbons and stack them on top of each other, you'll get pencil lead, right? But that's not an organic compound. So really, you're going to have carbon, hydrogen, oxygen, not all required to make it considered organic, but carbon is certainly the basis of organic compounds. And even when you look at this pile of models, if I tell you carbon is the black, you can just see that every one of them, except for these, which are not organic, are organic compounds. Okay? So, and if it doesn't have a carbon in it, it cannot have the name organic attached to it. Okay? So basically, C to C is our primary structure for organic compounds. So functional groups are organic molecules that have two parts, like a carbon backbone that really doesn't have much reactivity, and like basic carbon hydrogen backbones. Let me silence my phone. I had it on so I didn't miss the lecture ended. But let me silence it now. But then when you start adding stuff to it, like a functional group, that's where a lot of the characteristics of that compound come from. So a functional group is a set of atoms bonded together in a specific way, and they largely define the chemical and physical properties of that compound. So when we compare one organic compound to another that both have 3 carbons in them, if the functional groups are different in the two, it doesn't really matter that there's 3 carbons in each. What will define what that compound does or the effect it has is really about the functional groups. Let's move on. So hydrocarbon and carbon functional groups are basically standard hydrogen and carbon things. So it gets really confusing because when we talk about backbone, I saw her wiping with a cloth. Is there no? Oh no.
Oh, here.
No eraser in here?
She has an over towel. Here.
Is that what she was? Thank you. We need to get an eraser in here. There's always an eraser. It's the new room. It's the new design. Thank you. Because I do a lot of drawing in this class. But basically, it gets a little confusing because we talk about it as like the parent chain, and yet we still call it a functional group. By and large, when we talk about hydrocarbons, think of them, it'll be a lot easier for you to not to think of them as functional groups as much as thinking of them as like the parent compound. But we're talking about alkanes, alkenes, and alkynes. So alkanes have no double bonds. Alkenes have a double bond, and alkynes actually have a triple bond. And then we have our aromatics. So when you look at, like, where's my black? I always use black in this lecture. Where's the one I pulled out earlier? So generally, for alkanes, you'll have a series of carbons bonded together with no double bonds. If we want to make it an alkene, we're going to add a double bond somewhere. And if there's an alkyne, we'll actually have a triple bond. What does that mean, a double bond? It means that instead of you just sharing a pair of electrons, you're sharing 2 pair. Or a triple bond, you're sharing 3. And they're not, you know, instead of sigma bonds, you get pi bonds and all that craziness. You don't need to worry about that. But the bottom line is there's multiple carbons shared. One of the things that is a little bit difficult for some of you is looking at different ways to write the same thing. And so I'm going to write this, I'm going to take the changes back into an alkane. And I'm going to write this several ways. First of all, anybody know the name of this? Pentane. Okay, and we'll get into naming soon. But pent stands for the 5 carbons here. It's an alkane, so I'll have the name ane. But I'm going to write it this way. Okay, I'm going to write it this way. Did any of you know that there were H's on this first one or the second one?
Yes.
You did. Good. Because it's implied when it comes to organic chemistry. Whenever you know carbon has to have 4 things, you know it every time it has to have 4. And if nothing's there, it's an H. Okay? Just that's the way it is. I'll write it this way. How else can I write it? With the H's around it as well.
Do like the Lewis dot structure.
I could do this. I could also write it this way. The only reason why it's written this way is because it's taking a little bit of the geometry involved because those 3 H's are actually on this side of that carbon, but this is the same thing. I do have 5 there, right? Okay. You mentioned Lewis dot structures. I probably won't do that. It's way too hard. Anyways, there might be some others we think of, but these are all different ways to write the same thing. Okay. Where it gets really tricky when you get into some of these down here is if I were to do this. I took that 2 away, and now there's just 1 H here. And you're going to have to intuitively figure out something's amiss here. So you're going to start writing it out. You're going to go, okay, I got my CH3, and then C to C to C to C. And I want to fill everything else in here. Yeah, here's another way to do it, where you just do it straight up and down. But something's wrong here. This carbon only has 3. Now, I did say that if there's nothing there, then you assume it's H. Well, not if I'm giving you the H's. If I'm actually telling you the H's and there's an H missing, there's another explanation. And the only one you can come up with is a double bond. So this is actually an alkene, all right? And then you have to decide which side is the double bond here. Well, it can't be here because that means this carbon has 5 different things. And this one only has 3. And then this one has, so actually I miswrote this. So actually, I can't do that. I'd have to do that. Okay? All right? So now the only explanation is a double bond there. So that's where it gets a little tricky. You'll find some other stuff like with like carboxylic acids. There's some implied stuff. It gets a little tricky there too. Okay, so that's the basic chain. We'll get back to those. Some other common functional groups are alcohols, ethers, esters, aldehydes, ketones. I have some more slides about this we'll get to a little bit later, so I'm going to kind of fly through all these. Amides, phenols, aromatics, yada, yada, yada. Let's get back to alkanes. It's the simplest functional group. Older name for alkanes is paraffins, like 1,2-paraffin wax. Most guys don't know what I'm talking about, but I do. So. No, I'm good. And don't make my nails polished either. Just the massage, actually. So. Am I the only guy that's ever had a pedicure?
Yeah, no, I thought it's funny.
I've seen it in PT. I'm like, no. Just really, I'm only here for the massage of the foot, you know. So, but, you can trim them. but don't make them shiny. That's what I say. Don't make them shiny. So, anyway, all right.
We feel it awkward to beat each other.
So if you see the suffix "ane," that means you're talking about an alkane. The prefix tells you about the number. So you'll have to memorize some prefixes here. So the difference between calling it the parent group, ethane, versus an alkyl group. So this is the one part of this where remember I said it's better to think of it as a parent group than a functional group. When there are times where it's part of where you'll have a bigger chain and you'll have like a methyl group or which is an alkyl group or an ethyl group or a propyl group or whatever on there. That's when it's the actual functional group, and we'll get to all of that. Alkyl, just like alkane, so alkane is the more umbrella term. Ethane, the ethyl or F refers to the number of carbons. Same thing here. When alkyl just means it's a carbon chain, carbon, hydrogen, hydrogen, carbon chain, functional group, non-specific. Ethyl is more specific, 2 carbons. So like this ethyl chloride, Cl on there. So we got methane, ethane, propane. Let's add some more, like butane, pentane, hexane. Anybody know what the next one would be with 7? Heptane. How about next? Yeah. Decane. That's good enough. Really, octane is as far as you need to go. But those prefixes come from that, I don't know, Italian or whatever, or Latin or something, I don't know. So, Latin probably. So here's some more examples of what I was talking about, different ways to write it. So look at this one right here. So we have a CH3, so no double bond involved here, because in the middle you only have 2 because you have a carbon on each side, right? The end ones have the 3. So CH3, CH2, CH2, OH. OH is an alcohol group. Also can be written this way. So when I did it here, those who don't know this, pay attention. It's very important. If I don't write anything over here, or write anything over here, then this last point is a C. But if I were to add an OH here, I'm not implying a C here. Okay? Be very careful about that. So 1, 2, 3, 4. No, just 4 carbons. This carbon is attached directly to that O. Okay? But if you don't see that, like as in the example number 2 here, or number 3, those endpoints are C's. CH3s is actually what they are. Okay? So be careful about that. So in this case, carbon, carbon, 3rd carbon, that's it. No more carbons. OH. Carbon, 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 OH. Now, the alcohol will carry the OL suffix. The prefix would be what? Propyl or prop. So propanol. This is this is actually propyl alcohol, not isopropyl alcohol. So, I don't think I make you name alcohols anything more so just like butanol or something like that. Okay. This one though is very nameable. This is what I'll do. So you take and you go. This is straight chain carbons. 1, 2, 3, 4, 5, 6. No funny anything involved with that, alkanes or anything like that. So it's hexane, straight up. This one, you used to have to be able to name it when it had multiple things going on. I don't make you do that. If there wasn't this extra guy here, I would make you name this. But I won't because it gets too tricky. But this is a good example of where you have your straight chain, and then you have a hydrocarbon functional group attached onto it. This is actually 2-methyl, 1, 2, 3, 2-methyl-3-hexene. But I don't make you do that. Yeah. All right. This is a ketone with this is This is a cyclohexane. Cyclohexane with a ketone. You don't have to name that either. Okay. So if you take a hydrogen from a group, from a straight chain, that's when it becomes that alkyl group. So they are stick-on groups that are attached to larger molecules. And so we replace the A with the YL. All right, so let's go with this. Let's spend a little bit of time on the naming process. It's like a step-by-step. So let's take this. I'll try to write where I didn't write. Let's do that. So you take, and let's do this. All right. Oh, I've thought of another way to write it. Another way you'll see this one, for example, is this way.
So that carbon is taking
The carbon's coming at us.
Carbon?
That hydrogen is going away from us. So just another way it can be written. This diagonal way is much more actually accurate to the tetrahedral shape that occurs with carbon to carbon. It never is in a straight line in real life, but really, if the one on the bottom there kind of shows how when you have that here, that actually you have in the straight plane, you have one coming at me and one going towards you, the other two. So
the new one that you drew is still a hexane or a hex?
Well, let's do this one in a minute here.
Okay.
So.
Oh, there you go.
Okay. So take this. Name the longest chain as the parent. So here we have all these carbons, but we want to start from one end and get to the other, and we want to see if we can count the maximum number. All right. So what I mean by that is, in this case, it'll be the same. We'll go 1, 2, 3, 4, 5, 6 carbons. What if we start with this carbon instead of this one? 1, 2, 3. No, that's only 3. We had 6. How about this? Go this way. 1, 2, 3, 4, 5, 6. 6. So we come up with the longest number. And whether we use this carbon or this carbon as part of the main chain, we have 6. Doesn't matter in this case. So we have hexane. We know that. All right? And then we look for anything like alkyl groups, halogens, or anything on there to name on top of that. So what we say, okay, whether we use this carbon as the main or this one, and I'll just use this one to keep it simple, we look for add-ons. So this is an add-on carbon. And yes, there are 3 hydrogens here. There are hydrogens all over the place on this thing, right? I'm just not drawn. So we have this extra guy on here. And so it's an alkyl group. And how many carbons are part of that group? 1. The prefix for 1 is meth. So it's a methyl group on there, all right? So we have a methyl group on there. And we'll do it in alphabetical order. This gets really into it when we deal with halogens. Then we use multipliers to indicate the number of identical substituents. So if there were like multiple methyl groups, we'd add that on there. We'll get to that. And then we number the parent chain beginning on one end, not in the middle. So we either start with this is 1 or this is 1. And the key is to keep the numbers for the add-ons small. So indicate the constituent position with the lowest possible number. So if we start here and we go, this is number 1, 2, 3, 4, 5, 6, then that means this methyl group is on the 5th carbon. If we start over here and we call this 1, 1, 2, 3, 4, 5, 6, that means this methyl group is on the 2nd carbon. So we start over here. So it's 2-methyl hexane. So let's take this one. It's a little bit more. All right? So, what's the first rule? Longest straight chain. So let's see here. Let's start let's start with this carbon here. We could go 1, 2, 3, 4. We could go 1, 2, 3. We could go 1, 2, 3, 4. We could go 1, 2, 3, 4, 5. Well, 5 is our biggest number so far. Well, let's start with some other endpoint. We can start with that one up there and we'll find the same results. If we start with this one here, 1, 2, 3, well, it looks longer here. It looks like going through a maze. 4, 5, 6. Anybody see more than 6 anywhere?
No.
So 6. So when you're doing this, once you figure that out, write the word hexane. Because that is your primary molecule, your parent chain, and it's this section right through here. Okay? What's step 2? Identify functional groups. Well, if this is our parent chain, you have to look at everything else that's not just a hydrogen, right? So we got one here, we got one there, we got one there. What do we have? We have a methyl.
Dimethyl.
Okay. Yeah, I started as soon as I could. I didn't know if you were coming or not. So if you want to, set up, you can, and we'll switch over as soon as you're set up. So we said methyl. Which ones are methyl? All of them, right? Every one of these. This one, and this one. So let's write the word methyl. And what I do is, as soon as I see something, I write it down. And then I go, okay, what's the next one? Oh, it's a methyl, okay. Oh, the next one's a methyl, okay. What's the next step? The numbers, like how many of them?
No, they. Where
1 to 3, I'll make sure which
Lowest number. Okay, so we know our straight chain. So if we start here, 1, 2, 3. Okay, one's on a 3. 4, one's on a 4, and another one's on a 4. 5, 6. So 3, 4, and 4, right? But if we start here, 1, 2, 3, 3, 4. See how that's smaller? So 3, 3, 4, and then what? We give that prefix to the methyl for the number. It's trimethyl. 3, 3, 4 trimethylhexane. Yeah?
Why, so when I was counting the 1, 2, 3, if you come from right to left. You
On
have
the bottom?
Yes, from the bottom.
1, 2,
1,
3.
2, 3, and 4 for the next group. And if you come from left to right, it's 3 and 4. So
Right.
why?
How many? Okay, let's do it from the other way. 1, 2, 3, 4, 4. So our numbers would be 3, 4, 4. Instead, we were able to do 3, 3, 4.
Because it's lower.
So the total number, like we get more 3s this way.
Okay.
See that? All right.
This is a stupid question. Right?
Nah, I doubt it.
There's already 3, 3, 4. There's already 3 numbers. Why do you have to put try? I mean, I know this is the way they made it, but okay, it's just the way it is.
Yeah, I guess there might be a reason. I don't know. So now cycloalkanes. I do, in general, only in the basic sense, want you to name these. So it's a very similar thing. So let's start with this one. Parent chain. Well, we can start here, but we're going to really deal with this cyclo. So 1, 2, 3, 4. No matter where you want to start, there's 4. So it's cyclopentane. Did I say pent? I'm sorry, butane. Cyclo. Good, thank you. Cyclo. Cyclobutane. All right. So we have cyclobutane, and then we need to name what we have connected to it. So what do we see here? Do we see a methyl? Do we see any ethyl?
Yes.
Do we see anything else? So as we write this down, write it down alphabetically. So which will come first, ethyl or methyl? So write down an ethyl, write down a methyl. Okay? How many well, I guess next we do our numbers, right? And then we figure out how many of each, right? So we could start, let's say we started here. 1, 2, 3, 3, 4. Why don't we just start with something that's got something attached? So 1 will get something. So we could either go 1, 2, 2, 3, 4, or we could go 1, 1, 2, 3, 4.
1, 1, 2.
1, 1, 2, 3, 4. Now, you got to make sure you give the 1s and the 2s where they belong, right? So what do we have on the 1? Both ethyls are on the 1, and then the methyl is on the 2. And then how many of each do we have? So we have 2 ethyls, so it's a diethyl. 1, 1 diethyl, 2 methyl cyclobutane.
Is it important to put the little dash after the numbers? Are you that particular, you know what I'm saying?
This would be more appropriate.
For the test.
I probably wouldn't take either. But it's always better to be specific. Okay, this next one, it's a little tricky. First of all, what's the parent? Cyclohexane. And then we have a methyl group on there, right? So methyl cyclohexane, do we need to say 1? No. Because it will obviously be on the 1. There's only 1 there. So whenever there's just the 1, we don't bother even putting the 1. Okay. Now, if it was a straight chain, you would need to designate the location because it could be anywhere. But when in a cycloalkane, you're going to choose it to be the 1.
So the only reason you wrote 1 there is because of the 2 thing. You don't always.
On which one?
On the 1, 1 diethyl, you have to write it there.
Well, in this case, you have to,
Okay.
because you got more locations than 1 carbon. More locations than 1 carbon. So these ethyls could be anywhere.
Gotcha.
Once you have more than 1. But if you only have 1, why would you ever choose that to be the 2 carbon or the 3 carbon or the 4 carbon? So, this is really us choosing where to give the designation. And, I mean, we don't get to choose where that carbon is, but we can call any one of these 1, but only 1 is technically correct, and that would be to give it the 1. So it's kind of redundant. You want to switch? I didn't get the wrong stuff. Do I change anything on this thing? And again, it has the screen up, right? That's right. Yeah, I see it. It's there. Yeah, I know. It's not your fault. It's not your fault. I can tell you the class that I started I just sitting there when I got here and I saw you were here. I was like, I'm not sure you would normally be here, but I guess for tech you would be. They turned me away earlier. That's what happened. I was like, yeah, I know what you. Okay. All right, let's keep moving. Now press on. Press on. All right. Okay, so when it comes to alkenes, that double bond is the functional group. So you could have a generic formula where C double bond is C. What the heck is an R? An R represents who knows what. I'm basically telling you I don't know, I'm not telling you, or I don't care. One or the other. It's just something. It's something that continues on. It could be a methyl group. It could be a molecule this big. It doesn't matter. It's just something. The R1, R2, R2, R4 means that if you bother to give these two the same number, which is probably actually a typo, that means they are the same as each other. Okay, but this could be a 3. It could be, if you do give them the same subset, like the 1, you give 2 1s, then they are identical to each other. But that's all that R means. You'll see R a lot, and R just means it's something. Okay, so like take ethene, and then you're gonna have your alkynes. And you'll also see it this way, the R prime. So if you see an R and then an R prime, that just means that it's different than R. Okay. Acetylene. Anybody want to fire that up? Potato gun? I never bothered with acetylene for that. All right, now we have aromatics. So here's an example of an aromatic. So an aromatic is it looks a lot like cyclohexane. There are 6 carbons, but there's alternating single and double bonds to that aromatic. All right, and what that does is it actually makes it a planar molecule. A cyclohexane would have hydrogen sticking out both ways. The carbons would be, you know, even that would not be in plane, but the whole thing is in plane. The other thing we say about aromatics is actually these bonds exist in resonance, meaning it's not like this carbon have a double bond and this one has a single bond. Those electrons can kind of be shared with double bonds all around. So you'll see it drawn with the alternating double and single bond, like this, or you'll just see a circle drawn with just straight bonds, C to C to C to C to C to C with a circle in the center. Either one of those represents an aromatic. Aromatic is kind of like saying alkane. It's the universal term for when you see this structure. Now, if this structure sits here by itself, we call this benzene. Okay? All by itself is benzene. Benzene is a liquid. It actually is a great solvent for nonpolar substances. We don't do a whole lot with benzene in here. Okay? It's just not very human compatible. But anyways, but that's benzene. That being said, this structure is involved in a lot of anesthesia when it's attached to other things. For example, we could have this to an R group right here that continues on to form what we call phenylephrine. And this group, once it's a functional group instead of its home base chain thing, it's called a phenyl group, P-H-E-N-Y-L, hence the name phenylephrine. Or a lot of phenyl, different stuff you'll see, P-H-E-N-Y-L, phenylephrine. You'll see that structure all over the place in some of the drugs you give. And they won't all have the name phenyl in it, but it's around a lot. So, is there a way to switch which screen has my content? For me to be over here, and it's just, I mean, I can look at myself. Alkyl halides, this is also very apropos, where the functional group of the halogens, such as chloride, bromide, iodide, or very commonly fluoride. And you will see either the specific halogen given, or if you see, anytime you see X, that means it's a halogen, like universally, all right? So, so if you see R-X, you know you got a halide here. So example, methyl iodide, okay? We have, it's very similar to the structure I showed you last week, except instead of saying you have fluorine here, you have an iodine there. Okay? When it comes to naming, our inhaled anesthetics, that will be Dr. Wellender's lecture. But what we do have here is a halogenated alkane. We have this carbon. There's a carbon here. Remember, these aren't carbons because there's something, I wrote something here besides nothing, right? So there are no carbons here, but there's one here and there's one here. So it's an alkane chain with a bunch of halogens on it. And these 3 fluorines, and then over here we have a chloride, a hydrogen, and a bromide, and this is halothane, which is an inhaled anesthetic. And then we have over here chloroform, which we don't use chloroform. Criminals do, at least in the movies. I don't know. Yeah.
In your previous slide, you said methyl iodide.
Yeah.
Would it be wrong to make your methyl group your pairing chain, or can you say iodomethane?
Maybe. I don't know. I don't get too much into this, other than naming our ethers and that kind of thing. Because like in this case, what we did was we put all the halogens in the front and then left the ethane. So it probably would be fine, actually.
And do you
So
want us
like
to know,
iodomethane, yeah, that would be correct.
did you want us to know these alternate names like halothane, chloroform, toluene?
Okay, good question. Most of the ones I've given you, other than halothane, no. Like when I showed you acetylene, I don't care that you know that's acetylene, that's just for fun. When it comes to naming anything that's an inhaled anesthetic, I saved that for exam 1 because you have a lecture after the quiz on naming inhaled anesthetics. So, like, I will show you a few inhaled anesthetics today, but I won't get you to name those yet. Okay, so halothane, yes, but like chloroform, no, because it's not an anesthetic. So I'll try, if I have a special, like a more common name, I'll try to tell you. I actually expect you to know that.
Okay. And like, will you ask us to like draw the, like, say you tell us halothane, right? And then you want us to like.
After his lecture, absolutely. You have to draw it out, name it backwards and forwards, yeah.
When you're naming it alphabetically, does the di and the tri count?
No, you go with actually the functional group, and then, you know, so you can have a tri before a di, okay? So, functional groups based on water. These are functional groups where water was sliced off, and now you have some other group, like alcohol. So you can have anything to an alcohol. So that would look a lot like this. Matter of fact, if this was just 2 hydrogens where my fist is, anybody know what that would be?
Ethanol.
What?
Ethanol.
Ethanol. What is ethanol? Yeah, let's have some. All right. As a matter of fact, a couple of cohorts ahead of you have a shirt, like a UNF cohort T-shirt, and they put the chemical structure of ethanol on the back. So that was interesting. But anyway, so that would be ethanol. All right. Not to be confused when there's only 1 carbon, methanol, which you shouldn't drink that. Some people say you shouldn't drink ethanol either, but you know, it has its place. So, all right. Replacing the second hydrogen on water by an organic group yields an ether. So, and this is where I told you it would be good to prepare yourself for these so I can kind of fly through them. Like this, where we have a carbon to an oxygen to a carbon. Anytime you see that, you're dealing with an ether. So this is a halogenated ether. Oh my gosh, there's all sorts of halogens here. We got 3 here, we got 3 here, we have an isopropyl group here, a methyl group with a fluorine, and as a matter of fact, this is sevofluorine. Okay? And by the end of September, you'll need to be able to know that, name it, all sorts of stuff, but I'm not going to get into that now. But you would need to, if I gave you the structure on the quiz, oh yeah, halogen, there's some functional groups. There's halides here, and oh yeah, there's an ether there. You would need to be able to do that.
So when you're looking at that, I see the 3 carbons in a row.
Mm-hmm.
So if we're,
Like these 3 here, you mean?
yeah, right, isn't that gonna be the parent chain and then
So the
oxygen?
yeah. So what really gets tricky is when you start naming some of these, there's multiple ways you can name them. Like you can name this with like where you make the ether the functional group and then deal with this, or you can make it where these are the functional groups and make the ether kind of like the end of the name. It gets really crazy. And so that's where the great news from here on out is, yeah, I make you name some of these basic structures like we do. From here on out today, unless I tell you otherwise, you just have to identify what functional groups are there. Okay? So yeah.
So yeah.
Yeah. So yeah. Exactly. Like I said. So alcohols, you got so the alcohol is also a hydroxyl group. So you can call this part the hydroxyl group. Don't get confused because I have that oxygen in there. But it's an OH alcohol, hydroxyl group. So this is the example. This is ethanol, written in a different way. All right. So methanol, ethanol, propanol, octanol. Isopropyl alcohol, the only difference is this C has 2 C's branch off as opposed to a straight chain. That has the iso. You know, just so you know. Hey, I thought it was different. Okay, ethers. So you have that oxygen bridge. The key is when you think you see an ether, ask yourself, are the ether carbon that's attached to this oxygen got something else going on, like another oxygen? Is there another oxygen around? Is there a double bond around? You shouldn't have any of that to be an ether. I'll show you the difference in a minute.
Wait, can you say that again?
When you look at this and you see this oxygen bridge, you look at each carbon attached to the oxygen and ask, is there anything else going on here? Because you see COC, you notice that, the COC, but you have to ask yourself, is there something else going on with one of these C's, like a double bond to something, or an extra oxygen there or something? That changes the ballgame. You're no longer looking at an ether. And you'll see what I'm talking about in a second. See, here's an example of where you use the ether almost as a parent. Yeah, you can flip it around. So, like here's sevoflurane, here's desflurane. You see with each one of these though, the carbons that are on each side, there's no other like double bonds, oxygens, anything like that involved. It's just COC with nothing else crazy going on other than halogens. Okay? All right, an amine. Notice when you deal with, in blue always is the nitrogen. One thing about nitrogen is where it is on the periodic table, it needs 3 electrons to be stable. So this one, this nitrogen, chose to bond with 2 carbons and a hydrogen to get to share those 3 electrons. But there's 8 valence electrons, so 2, 4, 6, there's an extra 2 here. Just like with your water, even though we don't put the 2 little white sticks on there, this water actually has 4 electrons sitting over here by themselves. Valence electrons, right? So the carbon, whenever you see this little guy, that means 2 electrons. So those electrons being negative kind of push all those positively charged hydrogens down and make it this angled structure. But an amine is a nitrogen with 3 things bonded to them. No double bonds, no oxygens, just the nitrogen and 3 other things. They could be hydrogens, they could be R groups, like something else, it could be a long chain, who knows what. This is an amine. Not to be confused with an amide. We'll get to amides.
So it could be a carbon, or
Could be a hydrogen, like in this case, carbon, or it could be 2 carbons, or it could be a carbon, and then some more oxygens or something. But the carbons that are directly attached can't have like oxygens on them for it to be an amine. All right? Carbonyl functional groups are where you get the oxygen double bond to a carbon. And there's a couple of different ones I have here. Like we have this one here. We have another one here. Another one here. Another one here. And another one there. Look at all those. Where you have something to C to something and a double bond O. What these somethings are has everything to do with which functional group you're talking about. Okay? So, if there's none, well, here's a list: aldehydes, ketones, carboxylic acid, esters, and amides. Okay, but if you only have a C to C, okay, with no oxygens or anything like that, it's called a ketone. Like in this case, propanone, acetone. You don't have to name it, but you do have to recognize that this would be a ketone. Because when you look at the neighboring carbons, there's nothing funky going on there. No oxygens, no double bonded oxygens, no OHs, nothing. But also, they are carbons. Because if like one of these carbons was not a carbon but a hydrogen, that changes things. So C to C to C with a double bond O in the center. And the 2 C's neighboring don't have anything going on, ketone. All right? If you have like a C to C, the double bond O, and then it stops. So like where I took this and lysed it off and just put a hydrogen here, like I have one, I think. Yes. Like this, where I took this and turned it into that. So this comes off. Now it doesn't have C on one side. It's no longer a ketone, it's an aldehyde. We don't have a whole lot of aldehydes in our world. Okay. Carboxylic acids, you'll see a lot of those. So carboxylic acids are that one I kept showing you, and I kept hiding the double bonded O's to call it ethanol. All right, now this is a little different here. This guy right here is, you got the C, you got the double bonded O here. So C to C, double bonded O, but instead of a C here, we have a hydroxyl group, like an alcohol. This is a carboxylic acid. So C to OH. This is actually acetic acid. So you might need some vinegar. Esters. Look, they sound like ethers, they kind of look like ethers, but not really. Because here's your ether, C to O to C, C to O to C. But look at those C's, and one of them has a double bonded O on it. That ain't an ether. Okay, something else is going on here. So now, whenever you see that C to O to C, and one of the C's has a double bonded O on there, ester. Really, the only ethers you'll ever see in our world are your inhaled agents. You'll see a lot of esters in a lot of drugs. Okay. Ester is a very common thing. So yeah, back to your question. No, you don't have to name this. You don't have to know those names. For fun. Is it fun?
Yes.
All right. And then to compare the amine to the amide, if this guy didn't exist, that's in my fist, that's clearly an amine. Whether you have 2 carbons, 3 carbons, or 1 carbon bonded to this nitrogen, that's an amine. But because this carbon has a double bonded O on it, it's now an amide. So, I'm going to ask you to, this is a very common thing I would expect of you, to name the functional groups on this structure. And before we even go further, one of the things I'd like to point out is when you see this structure like this, you'll see this sometimes, from time to time in drugs. Okay? This is a very unique looking structure. We have this aromatic and then this chain of cycloalkanes, steroid. When you see a structure like this, you're looking at a steroid. Another big clue is when you see this diol in the name, the generic name, it's a steroid. Now, there are some steroids that don't have diol in the name, but when you do see it, you're looking at it, a steroid. We give some drugs that are like aminosteroids that don't have the diol name, things like rocuronium, vecuronium, the now goodbye pancuronium, all are aminosteroids, but in that structure, you'll see something in there that looks like this, steroid. But we don't, for purposes of this, we're not calling that a functional group or whatever. But what I will do, like on a test, is I'll say, identify the functional groups you see here. And so that's what we're going to do here today. And we'll start with you. And you always want to be the first one on a structure because you get to pick any of them, right? So why don't you start? Okay, so this is where you got to be careful. That's what I was saying before. This, exactly like this, and only exactly like this, is benzene. Whereas what you have here, you have a couple things. One, you have this thing on here, and then you've got something else going on here, so it makes it not benzene. Phenyl is even tricky because for phenyl, it has to be the end point. So let's keep it way more generic than that. What did I say it is in general? What's the umbrella term for any time you see this structure? Aromatic. So that's what I'm looking for in this. It's an aromatic because you know, we could get a name it, and I don't frankly know how to name it, right? So, I mean, at one point I did, but I a long time didn't care for you to, and I forgot to. So, but anyways, but it is an aromatic. Now, if there was a double bond missing here, it is not an aromatic. It has to have the complete trio of double bonds and single bonds in residence, okay? All right.
There's 2 hydroxyls.
2 hydroxyls, good. So you could say hydroxyl or you could say alcohol, either one. So here and here. Okay.
There's an alkyne.
An alkyne here, yeah.
That's what I was going to say.
There's one more I can think
Yeah,
of.
the methyl.
Methyl group. And, you know, keep in mind that you might get on a test a multiple choice where I don't say methyl, I say alkyl. Okay, so like you can I don't really care for this purpose what you say, but just know either way, right? Alkyl is the more umbrella term for this alkyl group here, which happens to be a methyl group. Okay.
So
Yeah.
alkyl and methyl, same.
Alkyl, no.
Okay.
Alkyl is the umbrella term
Okay.
for any hydrocarbon functional group. So methyl is always an alkyl, but an alkyl is not always a methyl. Okay. Does that make sense? An aromatic, a benzene is always an aromatic, but an aromatic is not always a benzene. Okay. It's the umbrella term versus not. Let's draw some Venn diagrams.
So
Yeah.
you wouldn't say that was phenol because why?
If for it to be a phenyl, it needs to be, let me just do it here. It needs to be connected to one carbon to some, so phenyl would be this R. It could be whatever. I got one coming up here, all right? So that's the only way. It can't be like double connected, or it can't have like, once you start adding other things to it, it gets really tricky, okay? So when it's the functional group, that's all by itself connected to something else, now it's a phenyl group. See that? But even if we started adding stuff here, now it gets tricky. I just what you say aromatic. Okay. All right. So where are we? Last slide. Well, yeah. Okay, we'll go this way then.
Sorry.
As an amine group for the end.
So here you're calling this an amine. So to be an amine, we have to make sure that none of the carbons it's connected to have anything going on with them. Do any of them have anything going on with them, like oxygens or anything? No. So this is truly an amine, right? All right.
An ester group?
You see an ester group. Tell me when to stop.
Stop.
Okay, so you're calling this an ester group. So you have a C to C to O to C. So really here, COC, right? So it sounds kind of like an ether, except that this C has a double bonded O on it. That's not an ether, that's an ester. You having trouble seeing it?
Yeah, I just didn't. I saw the other
Yeah.
one. Like,
Okay.
That
So-
I. Yeah.
Show one more time.
All right.
Yeah. I did.
This is a C here.
Yeah.
To C to O to C. So COC, you think ether, right? But you have to look at the neighboring C's, and this one has a double bonded O on it. It's an ester. All right. How about you?
I see another ester.
There's another ester here. So C to O to C, and that keeps going. So, but this one has a double bonded O, another ester here. Okay. And the only other thing was we could say a cycloalkane here, and that's what I would make you. That's what I'd be looking for. A cycloalkane. It's actually 1, 2, 3, 4, 7 cycloheptane, but cycloalkane is all I'd be looking for.
Can you go through, so what's going on over there with the and the funky line going down?
Well, what we have here is a nitrogen bonded to 2 different carbons that are part of the cycloalkane, but that's irrelevant to this nitrogen. When you look at this nitrogen, it's bonded to 3 R groups.
1, 2, 3. Okay. All right.
And none of those R's start with a double bonded O or anything like that, otherwise it's an amide. Okay? Yeah.
Would we also call this is also an aromatic?
It is an aromatic, but in this case, it actually can get the more specific name phenyl.
Yeah. That's a
Phenyl.
Yeah.
Because it has one going off at that.
Yeah, because it's just connected in one point there. Okay? So either one is acceptable, aromatic or phenyl in this case. But sometimes phenyl would not be acceptable. Okay? So we got some penicillin G going on here. So do we leave off with you or are we on Steve? You get to be first. That's always the best.
Is that an alkane?
Well, one thing we'll start with is, whether it be in here or in clinical, try not to ever ask questions when you're answering a question. All right? So start with a statement. I believe or I know that is an alkane.
Yeah.
So where do you, first of all, alkanes we would not say is a functional group. Now, if you're talking about an alkyl group,
Okay.
where are you talking about? Tell me where we're talking.
Yeah, starting on your left side there.
Okay?
So
Tell me when to stop.
No, you're going
Alright,
too
fast.
far. You're CH2.
This.
Yes.
Okay, so that's what you're trying to say, alkane. So when we talk about identify, this is more like the parent going on here. So the only time we'll talk about alkanes in terms of functional groups is when they're attached. Okay? So this is more the core. So no. So come up with something else.
Double bond carbon.
I'm going to pick something for you. How about what's this?
I'm not sure.
All right. I mean, just for everybody. See this here? We have this, what do we call it here? Aromatic phenyl group, right? It's an aromatic in general, and it was a phenyl group because it was attached directly to an R group. So it was this dash R, which looks just like in here, this dash R. So it's phenyl group.
Yeah.
Aromatic phenyl group. All right, go ahead.
Carboxylic acid.
Carboxylic acid. Tell me when to stop.
Stop.
Okay. So you're talking about right here.
Yeah.
So we have a C to OH, which looks a lot like a what? Alcohol, except that this C has a double bonded O on it, carboxylic acid. Okay? All right, let's keep going on.
Oh man, that's interesting too.
Yeah.
There's a lot more here.
Yeah, there's a ton going on.
Ketone?
Well, he's working on that, yeah.
Okay, so the aromatic group, are you saying that the phenyl, like PHENYL?
Mhm. Not to be confused with phenol, PHENOL, which would be just this dash OH, which I also think you should know. Phenol. If all of this was just an OH, that's phenol.
So the aromatic OH.
If all of this, starting with a C, turned into an OH, phenol. All right, they done helping you? Nice move, guys. All right, go ahead.
Is there an oh, there's an amine.
There's an amine? Okay, let's see. Moving along. Tell me when to stop on my amine.
That one?
This one. The way you said it was almost a question. Okay, so you're calling this an amine. So we have a C to an N to another C to another C. You have to look at the neighboring C's, the ones that it's attached to. So this C goes to more C's, fine. This C goes to an S. What about this carbon? Has a double bonded O on it. Not an amine. This is where I'm telling you, the amine, amides trip people up.
Sure.
That means they're esters, okay? So this is not this guy, it's this guy, amide. Okay? All right? What?
Does that mean that there's not an aldehyde in that? Because
Where do you think there might be an aldehyde?
no, I'm saying there's not an aldehyde.
You talking about like in this? Like in this one, or?
No, in the penicillin G.
No, I don't see an aldehyde.
Because
I don't think, I don't see one. Yeah.
This is a little off topic, but is that phenyl group what you call the beta lactamase ring when you talk about like a
This is the beta lactamase ring right here.
Oh, okay.
Yeah.
Oh, I can't see it.
So
Okay.
this, what I call the house with the garage, this is what beta lactamase inhibitors look like.
Okay.
They have that same structure. Cephalosporins also have a similar, not all of them, but all penicillins have this little house with a garage thing. And just a little, this is a little side, but it's fun. Your combination penicillins with a beta lactamase inhibitor, the beta, like the for example, clavonate in augmentin oxalin, basically is this structure without all this other stuff, a little bit of other stuff, and it's just a decoy. That's how it works. The beta lactamase enzyme that breaks down amoxicillin attacks the amoxicillin and the decoy, and you get a more amoxicillin available. Cool stuff. So that's a total aside though. All right. You're not off the hook.
Multiple alkyl groups.
Couple alkyl groups here, here. I think that's it, right? 2 of them. Okay, good. We'll not worry about the sulfur. Sulfurs, depending on how they're structured, could be a thiol group, but we'll just leave that out. I see one more. Did we go over this one yet?
No.
No, like after the
So
aromatic.
I want this one and this one identified. Actually, sorry, there's just one here. It's not this. I want this one here identified. What do we got going on here? It's an amide. Are we on you? Yeah. It's an amide, right? Because you have the C, you have the N branching out to a C, to an H, and a C, and that's okay. They don't have to be C's. You're thinking amine, but one of the neighboring C's has a double bonded O on it. Amide. Okay? All right, moving along. Now, once we get into this, we won't call it a phenyl group anymore. Go ahead.
Aromatic.
So you're going to call that, you're going to choose this one? Aromatic.
Aromatic.
Good. All right.
It's great being
You see hydroxyl group. There's actually a ton, right? But do you see any that are not hydroxyl groups, like not OHs? Just checking myself too. I don't.
I have no idea.
So all the OHs are hydroxyl groups. You have to watch out though, because some of the OH, you see an OH, you might think it's hydroxyl group, but it might actually be like it could be carboxylic acid or something. But all these are alcohols or hydroxyl. I will look for either name there. Okay, moving along. I don't remember your name. How you doing?
Oh, Valerie.
Valerie.
Sorry.
Moving on to you.
I was looking up, is there an amine at the bottom that never has oxygen?
You're wondering if this is an amine?
Yes.
So this is where you you need to try to draw this thing out in your brain. This is where it's a little bit more advanced because it's not showing you the structure of this, right? So you sit there and go, okay, we have a C to a C, to an O to an N to an H and 2. The problem with that is we're giving you these other hydrogens and it just doesn't make sense. This one's really tricky. This one's really tricky. So what you're actually looking here is C to N. This O is double bonded to this C, and then this N has 2 H's on it. Really tricky.
Yeah, it's not right here.
So now that I told you that, what is it? Amide. That's right. All right. What else we got?
Ketone.
Yeah.
Okay. And I will, in this case, agree with you. I will warn you. Anytime you think you see a ketone, put your big red flag up because there aren't a lot of them out there. Okay. Especially when you're looking at any drugs out there. There's, you see the double bonded O. It looks like it's all good, but in this case, I will give you that is a ketone. Only because even though there's an OH here, there's no double bonded O on this. So there's one here. Oh yeah, there's 2 of them. Here and here. All right.
Those are ketones?
Yes. I know, there's all this other stuff, but really when you look at the neighboring carbons of each of them, there's no double bonded O's on them. Okay?
It's hard to see.
All right.
An amine group.
Yes, that's an amine. That's right. You got this nitrogen. So one methyl, another methyl, and then this carbon here, that's an amine.
You did say that was a ketone, right?
Yes.
Yeah, okay.
Ketone,
Just wanna make
ketone.
sure.
I think we got one more. I don't know if it was said or not. Got it? I'll just say, because it might have been said, an alkyl group right here. Anybody see anything else? All right. Okay. So you will be given similar structures, and you'll be asked to identify those functional groups. All right. Stereochemistry. You had Dr. McDonald's lecture already on this, right? On hydrocarbons and enantiomers. No? Yeah, I thought so. Is pharmacokinetics and dynamics lecture?
That's right, that was a blur.
It was a big blur.
He was not nice.
I don't remember much, but I remember
He
I
was
said.
very nice.
Yeah, that's what he was. I wasn't here, I can tell you. That's nice. I can just tell you that right now. So, enantiomers. So I'm going to kind of get into it with you. What does it mean? What are they? What's the deal? What? He gets a lot into why is it important. I want to get to more explaining how you define them. Okay? So we're going to get really into the chemistry of stereochemistry. So first of all, let me just take a minute to talk about isomers. Okay, an isomer is where you have two different compounds with the same chemical structure that might have something that's different about them. For example, these two isomers have the same number of carbons, the same number of hydrogens, but structurally, they're different. Just like when we talked about methyl groups, when we named them, we could put the methyl groups in different places, and they would have the same number of carbons and hydrogens, but it's an actually different structure. That would be like a structural isomer. All right? You can have also geometric isomers, where not only are they the same carbons and hydrogens, but they actually have the same formula. If you were to draw this out, you'd say CH3, CH, CH, CH3, CH3, CH, CH, CH3, but they are not the same compound. And you can't flip these around. Now, one thing you probably have already seen me do is spinning things a lot. Well, you can spin single bonds. And what will happen actually to this compound is as it sits here, it will try to orient the hydrogens in the way that they like to be the most, either away from that oxygen or towards it. If they like being closer together, you'll see it spin to where it gets the most happy. For example, looking at this, you won't see it oriented this way because that fluorine is closer to that oxygen. They don't like that. So they'll try to get as far away as possible, and by being turned this way, there's a little bit more distance there. Okay? And then this one, same thing. So this is typically how you would see this one oriented. And this fluorine might be very happy near that hydrogen there, and that's probably how it'll be set. And you can spin these around, and with some of them, spinning around doesn't change the compound in any way whatsoever. But when there's a double bond, you can't flip them. They don't just automatically flip. And so therefore they are one or the other. And the cis versus trans just has to do with whether or not they're coming across or directly across that way. So these are geometric isomers. We don't deal a whole lot with structural geometric isomers when it comes to practical chemistry for pharmacology. But stereochemistry we do. All right? And that's where we get into things like chirality, where we have actually the exact same structure. They look totally the same, but they're not the same. They're mirror images of each other. And when you hold out your hands, despite, especially if you haven't aged much, because the more you age, the more you get aging flaws. Or I know this ring actually fits a little looser on my left finger than my right finger or whatever. But pretty much I can say these are identical. I do know I have a little bit better veins on my right hand, which that kind of thing. But anyways, but they're not identical. And the reason why is because even though I want to go, yeah, see, they're the same. They're not the same. Because when I try to look at them from the same direction, like this dorsal side, for example, in this case, the posterior aspect of my hand, right? This is anatomical position. They aren't. They look the same. They're mirror images, but they're not. And so I even have these two structures to help you out here. I'm holding a hydrogen in my hand. And then I got like a chloride, and an iodide here. Bromide, iodide. Let's say bromide. Chloride, because that's more common. Chloride, bromide. They look exactly the same. But if I try to what we call superimpose them, where I match up the hydrogens and I match up the bromines, they don't match. Those are what we call stereoisomers, where they mirror each other, but they're not the same. Stereoisomers are a subset of geometric isomers that contain what is called a chiral center, the chiral carbon. The only way you can have it is you have to have 4 different things attached to that carbon. Once you have like 2 hydrogens, like a hydrogen and 1 and another hydrogen, you can't have a chiral carbon. Yeah.
You know the baseball bat and the baseball? Yeah. You're saying those are superimposable?
I'm saying the baseball bats are, the baseballs are, but they may not be the same. Oh, no, not superimposable.
It says it's non-chiral, so it should.
Oh, sorry. So these are non-chiral. So these, you could put one bat on top of the other, and they would look the same.
Okay.
You could put one baseball on. You could put one glass on top of each other, and look the same. But our hands, even though they're mirror image each other, so are these. You can't superimpose them.
I have a question about that.
Yeah.
That's not like a 2D level though. For the example, like what, you know what I mean? Like.
Well, you know, and that's part of where when you turn it around, that's no longer we're talking about 2D. These, hopefully, these things will really help you see that because they are 3-dimensional structures.
So it's just
you will not have ever a stereoisomer that's 2-dimensional. The very definition of a carbon that has a tetrahedral bond. Anybody know the bond angle of the carbon tetrahedral bond?
Used to. 105.
You're close.
120.
It's 108. I'm almost sure of that. It's been a while since I've even looked that up. But these angles here, 108 degrees, 108 degrees, they're basically as far apart from each other as they can get. And that creates what we call that tetrahedral structure. And so because of that, and because the rule for chiral carbon is you have to have 4 different things on it, you will never have a 2-dimensional carbon or structure. So anytime we're dealing with a chiral structure, it will be 3-dimensional.
It's like a flaw in the metaphor, not necessarily like we're trying to describe reality. Like that's what happens in reality, but it's just because like we have a lack of an appropriate metaphor that you can't explain it that way.
Yeah. Well, and you know, I don't necessarily consider my hands truly 2-dimensional. So, but anyways, all right. So these are actually these 2 structures are ones that are circulating around, and you can see that even though they look identical, they're not. So what happens is if you look at this structure down here on the bottom, when it comes to what we call that lock and key kind of thing, you have a receptor that is looking for this exact match. Only one of the 2 stereoisomers will match it. If you try to put this one over here, the square will try to go in the triangle. And the triangle will try to go in the square. It won't work. And that's why it's so important. So enantiomers, which are stereoisomers that have a chiral carbon, have identical physical properties like boiling point, melting point, density, but they don't have necessarily, they sometimes do, but they don't always have the same physiologic effect. Now, how are they identified? Well, there's 2 ways they're identified. One is the sinister and rectus, and the other one is the levo and dextra. If you took this a drug or any substance that has a chiral carbon and you put it through this polarimeter and it rotates to the left, it's levo, and it rotates to the right, it's dextra. That's where those come from. There's also the sinister and rectus, and those have to do with how they rotate light. But then the sinister and rectus is a little bit different, where they take the carbon. I have one that's higher. But the ones that are going on, they'll hold it, and there's like an order of priority based on hydrogen versus what halogen it is, or how many carbons and all. And they hold it, and whether or not they go clockwise or counterclockwise. You don't have to do that, but that's how it's done. So you can see the eye, and they hold it up, and that's how it's done. But going back a minute, the bottom line is, whichever system is used, that's how it comes up with it. Usually, a levo structure is a sinister structure, and a dextro structure is a rectus structure. That's not 100% true, but almost always it is. So levobupivacaine is also sinister bupivacaine. but that's not something you can universally say for all drugs. Okay, and what you'll find is one drug that has a chiral carbon we commonly use the levo or the dextro terminology, and another one we commonly use the sinister erectus, and it's just the way it is. But it can be either. So an example of a drug, well, how about like levothyroxine? Guess what? Where do you think that word levo comes from? What other words do we drugs? Normally I can come up with 3 or 4 that we. Levofed, perfect example. So there is that tells you there's a chiral carbon in there, and the levofed is the levo form of that chiral carbon. A racemic mixture contains equal amounts of both enantiomers. Therefore, if you put the racemic mixture in that polarimeter, you won't get any rotation of light whatsoever. It'll be net 0. That's a racemic mixture. An example of that would be racemic epinephrine. Now, that must tell you that most drugs we give aren't racemic mixtures. Because how often do you say racemic anything? Do you know a lot of drugs we give are racemic mixtures? Why don't we call them racemic whatever? Racemic bupivacaine. We never say that.
Maybe the racemic form is the only one that we use.
Maybe the racemic form is the one that we normally use. Because like in the case of bupivacaine, there is a levobupivacaine up there, and it's called levobupivacaine. But the bupivacaine we normally give is racemic by its normal use. And so drugs that we give that are normally racemic, that's the normal preparation of it, we don't bother to say racemic all the time. So that tells you that the epinephrine you normally give is not racemic. Only the epinephrine that's called racemic epinephrine is racemic. This is all part of that sinister erectus. You don't, it's just kind of for FYI. All right. So, the beneficial effects of one drug can therefore reside in one enantiomer, with its parent enantiomer either having no activity, some activity, the opposite activity, or a completely separate beneficial or adverse reaction. Who knows? Some examples. Racemic thalidomide was prescribed for morning sickness back in the 60s, but they later discovered that levothyroxine was very effective against morning sickness, but the dextro was extremely teratogenic. So they ditched it. But if they could have isolated just the levothyroxine, and maybe they could have, maybe I don't know. Maybe they're just too afraid by the time they realized it would have been fine. Okay? Here's a good example of a drug. Ibuprofen is a racemic mixture of 2 non-superimposable mirror image enantiomers, the rectus and the sinister ibuprofen. The majority of the effects of racemic ibuprofen come from the sinister ibuprofen. So we get both, but really most of the effects we get come from that sinister side. The rectus just doesn't do much. So probably it's just too expensive to isolate, and it's not that harmful to keep both. That's what I'm guessing. Yeah.
So in the drugs that say like levofed, it's only those?
Maybe not. It depends. You know. So probably, but there's no real guarantee because sometimes it's hard to isolate completely one drug. So especially when it comes to stereoisomers. So rectus methadone has a 20-fold higher affinity for the mu opioid receptor than sinister methadone. How many people knew there was more than one kind of opioid receptor? You may have ever heard of mu before? Mm-hmm. Anybody not heard of mu before? You can raise your hand. No?
Well, I read it in Wellette like 2 days ago.
What's that?
I read it in Wellette like 2 days ago, I think. In our pharmacology of anesthesia book.
Oh, okay.
I read it for the first time.
You read it for the first time. Well, my very first lecture with Dr. McDonough, that pharmacokinetics and dynamics lecture, he asked some question and somebody said opioid receptor. He said, which one? I'm thinking, how did he ask me? They said mu, and then he said, which one? I'm like, And then the person said like U1 or whatever, I forget what exactly the question was, and I was like, what the heck are they talking about? And I imagine each one of you had that moment in the last week or two, where one person answered the question, you're going, oh my gosh, I don't know that, I'm in trouble. Maybe not, probably not. You know, we all have things we know, and I'm not dying. Hey, look, if you don't know anything, everybody knows something. But if you find yourself constantly going, I don't know what they're talking about, maybe that is a sign you need to study more. Or maybe that's just something you didn't know. Bottom line is, when you realize there's something you don't know, go look it up. So,
Steady.
but no, it is completely normal for us to start throwing out terms that you've never even heard. Wait, calcium channel? There's more than one calcium channel? I was surprised I knew there was one. Yep, there's always another level. So anyways, rectus methadone has a 20-fold higher affinity for the mu-opioid receptor than sinister methadone. So here's an example of where the rectus, normally it's the sinister and levo that is the better one, the good cousin. So sinister citalopram has over 100-fold more potent inhibitor of serotonin reuptake transporter than the rectus. Cardiotoxicity of bupivacaine is mainly associated with the rectus or dextroenantiomer, which is why they make levobupivacaine. The psychomimetic effects of ketamine are more associated with the rectus enantiomer.
One question.
Yes.
Does this sinister and that have anything to do with cis and trans?
No. If you go back and look, I had the geometric isomer one is the cis and trans. That's totally different. Okay. So.
The cis and trans is just for alkenes, right?
Yeah, they were only for like double bonded carbons is where you'll see the cis and trans. And we don't really hardly ever do those. When we do, stereoisomers come up quite a bit. Where are my models? Did they get all the way around? Not
here.
quite?
No, they're right here.
Oh, they ended with you. Okay. So did that help? I mean, I'll challenge anybody to be able to actually make them superimposed. Like, okay, we got the, nope, that doesn't work.
Well, if you took them and folded one inside out.
I popped them out and put them in a different way, yeah. So I mean, but you can make all sorts of mirrors out of this. I mean, you can mirror them here. You can mirror them here, but you can't superimpose them. They're not the same structure. So. The last two slides are more practice. Y'all can do those on your own because I want to let you guys out soon because I know how bad traffic will be. As a matter of fact, those who are going to UFL today, if you leave now, you might actually beat some of the worst of the traffic. You're welcome to walk out, but I'll stay for questions.
I have a question and then one.